Kia ora and welcome, everybody. Yeah, thanks for joining us. This is our one of. Thanks, Robin. Appreciate you. Just got to get closer to the mic. Kia ora and welcome, everybody. Yeah, this is our New Zealand Antarctic Society Wellington Branch annual event, fresh off the ice. So really exciting time to get those kind of first stories, as they come off the ice. We've got four great talks lined up here. But I'll just start us with a couple of housekeeping items. So the bathrooms, if you haven't found them already, just out this door and to the left, you'll see them down there. And in case of any sort of emergency, we're going to muster over here in the parking lot, in the car park over here. But the fastest way out is going to be through those doors over there. And maybe you can grab some wine as you go. Don't know. Or the juice. Um, so for the speakers, for everybody online, everybody here as well, we are being recorded. So use your judgment as you make comments about wine and whatnot.
Sorry, I'm just
Um,
the people online.
And no, thanks, Natalie. But what that means for the folks online, if you have any questions, please chuck them into the chat or Q&A, and we'll get to them that way. And the folks here, just raise your hand, old school style. Yeah, so it behoove me not to mention the opportunity to join the New Zealand Antarctic Society and of the Wellington branch. We're looking for a few good folks to join us. So um, yeah, so a lot of fun opportunities, events like these. We've got other events, midwinter celebration, as well as other talks throughout the year, and awesome outreach opportunities as well. So yeah, get in there and join. So there's some flyers and some stickers over here on the thing there. So take that with you on your way. But yeah, so that's probably enough from me. We'll just get to the talks coming here. So looking ahead to the talks, I mean, we've got four amazing talks coming up here, covering quite a range of Antarctic science. And as a geologist, I was a little disheartened not to see any geology in the mix. And I had to take a step back and remember that ice is a rock. So everything's okay. And floating critters in the ocean and in the atmosphere ultimately find their way into rocks. So I'm okay now. Everything's all right. So without further ado, I think we're ready to start here. Svenja's going to start us off talking about zooplankton in the Ross Sea. Thank you.
Can people online see the slides actually? Do we know? Yeah, nice, excellent. Cool, awesome. All the pictures come up too. Awesome, how exciting. Yeah, I'm lucky today to talk to you. Thanks for the invite. Thanks, Natalie, for organizing it. Has been probably a lot of work involved. Yeah, I'm the zooplankton ecologist at NIWA here, so hence I'll talk a lot about zooplankton. And also here, I'm Dr. Svenja Halfter. How exciting is that? I just recently got my PhD, so that's why I'm still celebrating, right? You know, 20 years down the line, nobody cares, I guess, but I'm still like really excited to add this little doctor thing in front of my name. And also, this is just a good opportunity for me to show off some of my nice pictures. So I just like taking pictures. They're not really good, but I like taking them, so that's all. Who am I? Before we talk about zooplankton a lot, I grew up in Germany, as you can hear from my accent, where I studied biological sciences and marine biology. And well, this is me as a baby, not as a student. I grew up a bit, as you can see. I was really cute back then, but now, well, you can see it here. I was fortunate to spend over a year in the Arctic for my master program, and kind of the plan was to stay there for 2 months. But then, well, things happen, so I stayed for a bit longer. Here is me being a polar bear guard up in the Arctic, while everybody else is working hard on drilling to the sea ice and sampling the sea ice. And then I moved to Australia for my PhD in 2017, which I finished early last year. So yeah, now this little doctor thing in front of my name. And here this is me being about to embark on a 6-day walk through the Australian bush. Pretty exciting. And then now I moved to NIWA just in July last year, so pretty recent. And yeah, got a position here as a zooplankton ecologist and postdoc. Let's dive into zooplankton. What is zooplankton? What are zooplankton? Plankton means drifting, just I think it's Greek. And they're all organisms that drift in the water with the water currents. And you can see from my pictures here that there's a really diverse group of animals. So it's really diverse. And we have crustaceans, we have sea snails, jellyfish, even salps, which are some kind of jellyfish, not really related, but anyway. Copepods, lots of different things, and they're all quite important. Why are they important? They're really part of the base of the food web. They connect the lower trophic levels here, which is algae, the plants in the water drifting, with the higher trophic levels, which is all fish, marine mammals, and seabirds. As you can see, without zooplankton, we wouldn't have all the other amazing animals we love to see, like orcas, for example, and seals. And then also because they do a lot of, they migrate in the water up and down, not, they're drifting with the currents, but they migrate a bit up and down during the day. So they transport a lot of nutrients and carbon in the ocean. So that's why we are also really interested in them. And I got to be very lucky because just really soon after I started at NIWA, people were like, oh, let's go to Antarctica. And I went even twice this season. So I was super lucky. The first time went on the sea ice trip with Natalie, which will probably tell you more about it later, in October, November for 5 weeks with these amazing people. It was all great people. And then a bit under the sea in January, February, I just returned 3 weeks ago. I went on the Tongaroa trip down to the Northern Ross Sea. So yeah, I was just... Okay, right. Yeah. Let's talk first about the sea ice cam. We flew down to Scott Base in early October after a week of delays and waiting in Christchurch for a bit, and one boomerang flight. We ended up in Christchurch 7 hours later. It was exciting. But we were a pretty good team, so we went all through all the delays and issues, because then we could finally be deployed to the field and camped on the ice for I think almost 4 weeks. It's our container camp, and attached there were also some tents. So I think the second from the right is my tent. I slept there for 4 weeks. It was great. I was just adventurous. Never did anything like it. It was really cool. Really cool. Actually, it was really cool. Nice. All the puns. And then we had these Haglunds we drove around. I guess all of you would know, but just showed a nice picture because it matches with the green of the containers. Anyway, aesthetics. Aesthetics are important. All right. Our aim was there to sample the plated ice. And if you're like me, I didn't know what plated ice was because I never really focused on really close to the Antarctic continent. Natalie can tell you a lot about it because she knows everything, but really everything there is to know. Don't undersell yourself. But basically it happens as a marine biologist. It's a really simplified explanation. When the ice shelf melts, for example, the Ross Ice Shelf, there is super cold water, so that's water below its own freezing point. And if there's some nuclei, so where crystals can form in the water, there's this frazzle ice formed in the water. And because ice is less dense than water, it floats up, right? And we have this whole layer of platelets. So you can see they're really broad, but really thin. They they float up and bump up below the sea ice. So we build this beautiful layer of basic double layer. We have the sea ice, we have the plated ice. And as you can already see in the picture, it's really greenish. It's already a first indication there's a lot of life in there. So plated ice is thought to be a really important habitat for algae and also for zooplankton, because it's really protected from predators, but also has a lot of nutrients in there and sometimes lots of light. So it's really good growth conditions for animals and algae mainly. So that's why we wanted to sample the plated ice. And we were super lucky right here at NIWA. So many amazing people around came and just, met all these amazing people and really smart people. So Craig Stewart from NIWA and Natalie and team, they developed these plated samplers, a new tool. They tried it out last season again already, and tried this season to get some samples from the ice. And the really cool thing about it is it samples the plated ice, and it gets section by section up. And it has, the good thing about it is we have the crystals, but also the water around. So we have the whole habitat basically up in a tube. And once we melt it overnight, we can even see what's living in there. If there's some zooplankton and if there's some algae and what kind of nutrients on there. So we have this beautiful tool now. We tried out, and well, we waited a bit for it because of some plane problems, but now we got to use it quite a bit once everything was there. And so I can't really present you a lot of results because I've just been back from Antarctica again, so I didn't even have time to look at things. But what's apparent, at the first sight is we had lots of algae. We had so much green stuff in the water, algae, stinky things. But not too much zooplankton, surprisingly. So I was wondering, where are the animals? Because we saw also, when we drilled holes in the ice, we saw a lot of fish around. They must feed on something. But I didn't find many zooplankton in the ice. So that was interesting. I got a handful, but I expected it to be so much more. So that was, I guess, cool. But you can see there's a really high diversity of phytoplankton in the ice. So that's pretty cool. And first time we could sample it so amazingly with the sampler. Changing topics now. Let's go over to January, February, my trip to Antarctica. Just returned with some of you here in the room. We got to go all the way down from New Zealand, sampled kind of on the way south too, but we mainly focused on the northern Ross Sea, so between Coolman Island and Cape Adare. Had lots of coastal sites. There's lots of there was a lot of benthic work going on, sort of seafloor work, but I got the sample too, which was pretty cool. And my work included using the continuous plankton recorder. It's a tool we pull behind the ship, and it gives us a continuous record of zooplankton in the water. I guess that's why they call it continuous anyway. And then while we're at the station, I got to use the nets to the bongo net, which is just this double net. Which is just taking out the zooplankton in the upper 200 meters of water column. And the samples still need to be analyzed again because I just returned. I haven't had time. But this is, some nice pictures I showed, from things I caught. We had lots of copepods, these crustaceans, really small crustaceans up there. As you can see, they're really red, so lots of crustaceans. Pteropods, there are sea snails, chaetognats for arrowworms, siphonophores, type of jellyfish, fishies, of course. Amphipods, another type of crustaceans, some salps in between the algae mixture. A ctenophore, which looks really sad here, but it's actually really pretty in the water, prettier in the water than on the petri dish, and worms. So just a few worms here and there. So really diverse range. We had little issues on the way. So I think bongo number 5. You can see me before deployment, really happy, really excited. After deployment, well, you can see there's something missing. The net, the frame, thank God, came up, and the sensors were attached still, and everything was good. But the net themselves, they're on the bottom of the ocean right now. So, sorry, pollution. That's me. However, thank God I had a spare net, so I could continue my sampling, which is great. And another little issue. What I came for is this beautiful red soup of crustaceans and beautiful things, which I got also on the way south, which is on the transit. I got this beautiful soup of zooplankton, but then once we entered the Ross Sea, there was a soup of stinky, very stinky algae. My lab was always the most stinky on the ship. People were like, "Oh, Sonja, what are you doing in here?" Well, it's not me, it's the algae. So that was interesting to find actually more algae in my net than zooplankton. And that's quite interesting because it's kind of a trend that emerges from both deployments that very close to the coast don't have much, don't have many zooplankton. And I think it's weird because zooplankton usually, scoop my net through water. There's always something. It's not, they're rare. There's algae. They feed on it. That's it. But in our case, well, there were not too many. And the Rossi is very productive. You can see all these penguins and whales and seals and fish, of course, doing the other deployment. But, there must be zooplankton connecting the trophic levels, right? But I don't know. The question is, are zooplankton, more patchily distributed than previously assumed? Maybe it's the sea ice, because as we probably know, we have a really low sea ice here this year. I don't know, something is off, either this year or in general. So what I will do is I have some data, thankfully I have some data from the last years, and I hope to compare last year's data, or last, three or four voyages to data I got from this year, and hopefully I can figure out, what's really happening here. And then, yeah, I just want to thank everybody who has been involved, and there's lots of people not pictured here. But yeah, it has been such a great experience, and especially to Natalie, who just didn't know me before I even went down south, and now she knows me, I guess. 5 years on the ice, 5 years, oh gosh, 5 weeks on the ice does that to you, So thanks to everybody has been made it such a great season for me. So thank you so much, and thanks for listening today. Any questions?
Yeah, we've got a few minutes for questions. Anybody in the crowd? Anybody online?
Oh, people. Oh. So again? Potentially, yeah. I don't know, because I just started studying the Ross Sea. Before it was more like subantarctic, Southern Ocean. But so it could be that the sea ice plays a role here, but I have to figure that out. So the thing is, the last voyages, the very last voyage, 2021, went really close to the sea ice too. So hopefully I can compare the seasons. And then the other voyages before that, they're a bit more offshore. So hopefully I can just look at the numbers and see. Because yeah, as I said, there's lots of things feeding on zooplankton, but where's the zooplankton itself? So yeah, maybe yeah. Yeah, there was somebody with that. Yeah. I did expect to find zooplankton, especially because there was so much algae. When I was out there in October, November, I thought it was a problem of season. So when we were just too early in the season, maybe it was too cold. But also, well, we came really close to Scott Base because the sea ice was so low that we had to be really close to be on thick enough ice for our containers to, be deployed. Usually we would go a bit further out and, see also different locations, but our fieldwork, because of delays and flights, are really condensed into just a few weeks, almost less than 2 weeks. So we had to really make do with with the time we had. So we basically stayed really close to coast. So that's why, yeah, maybe that's the thing. Yes. Wow. So there's lots of questions about that. People were blaming me mainly. Maybe it's true. So first of all, we were really in productive water. So the more algae is in the net, the heavier it is. And then it was a bit rough that day. So we had lots of, currents pulling on the net. So I guess it was just a combination of both that the net was just not, because both popped off. I guess it was just too much for the net. And thankfully, the crew helped me to prepare the next net to we had lots of ropes attached so it doesn't pop off again. So that was really good. Yeah, also out there on the ice, it was just without people helping us and all the support staff, we wouldn't be out there really. So it was so good to be surrounded by people who are actually interested in helping you and getting you back on the track. Oh yeah, they probably have a look. Oh, oh yeah.
Is there a question over here? Yeah, go for it.
Yes.
When you're living in a tent out there,
Well, we were out on the sea ice. We were not too far from Scott Base, but we went in sometimes to, well, officially to do things, but also get a shower. We were, well, not, people run out, but we probably usually took the Haglunds. We were half an hour away, so not too far. We still didn't have a shower for 10 days between, so it was still too far to go every day, but yeah. Mhm. Yes. Not in my nets because the bongos are not good to catch krill because they're too slow. But there are some schools of krill, yes. So we caught them with the bigger net. And what was the second one? Sorry, I forgot again. Yeah, so near the coast, we didn't see many. I think we were a bit further away. We saw some krill on the acoustics because we have acoustic sensors basically, and we see if there's something in the water, and that's why we try to target it with the bigger nets. We target that and try to get it up. So we got some krill, yes. Oh my God. That's a good one. I don't know. I mean, I went on other field trips before, so I kind of knew what I got myself into. But especially after the sea ice, my body was just exhausted. You come back and you just, because you do a lot of manual things. And when you sit in the office the whole day, as I usually do, it's a lot. But I don't know. Yeah, it's surrounded by great people, and usually, I think I had both times really good teams to be around with. So I don't know, it just works out. Sometimes people figure out that they're not good for field work, and usually, these 5 weeks, 6 weeks trips are a good way to do it. If you don't like it afterwards, well, never do it again. But I don't know. I mean, otherwise, just be open, be kind to yourself, to other people, be patient. I mean, I hate being patient, especially with myself, but it's Antarctica time anyway. So if you say, well, we leave by 9, then we leave by 10 anyway. So and everything takes slower, and you have to take that in account that your body, you're in this, -30 outside, and it's cold, and it's sometimes horrible. Like, weather is not great, but I don't know. In the end, it's the best thing to do in the world for me. So I have the best job in the world. Yeah. Oh no, is that the question? What do you like better? I don't know. Well, I don't have to worry about polar bears in the Antarctic. You don't have to carry a rifle, which is really heavy, which is nice. Except if you don't like the people, but another story. I don't know. Otherwise, I think it didn't get, well, it got as cold as Antarctica too in the Arctic. So I don't know. It's pretty similar. There's a special type of people who enjoys these conditions. So I think I love both. I want to go back to the Arctic too. It's just great. I love it. Yeah. Anybody else before we move on to the next beautiful speaker? All right. Cool. Thank you.
Wow, really great stuff. Yeah, nice discussion, everybody. I mean, two seasons in one. Not bad. Yeah. So you've taken a break yet, or okay, good. Nice. No, I echo a lot of your feelings about the field work, and you know it if you're in it or not. Yeah. So we'll move on. We won't go far from the boat, but we will go to the atmosphere. Hey, so Emma. Yeah, thanks.
Cool. Hi, everyone. I was lucky enough to also go on the Tangaroa this season. Svenja was actually my roommate. So thank you for your background. I'm going to use some of that so that I don't have to talk about that as much. So my project was looking at the emissions, the biogenic emissions that come off the atmosphere, and how they get into the atmosphere, and how they interact with clouds and climate, and then also how they get incorporated into ice cores. As you can see by the amount of logos on the bottom here, this work was able to happen with a huge team of people. So thank you to everyone. This was a big component of Holly's, my supervisor's Rutherford Discovery Fellowship, and then contributions from the wider team. So a big thank you to Niwa and the Tangaroa and the people who provided a berth for me and the logistical support. And I would also really like to acknowledge Mike Harvey's contributions to the proposal. Cool, so we had a bit of background about zooplankton, and phytoplankton are similar except that they are plants and not organisms. So they are really important for the global climate systems, and they act as a really large large carbon sink. So as you can see on the right of the figure, they impact the carbon uptake, and then they also act as like a cloud seeding. When their biogenic emissions come off, they act as a cloud seeding particle. So when there's large biogenic emission events, there's often more clouds associated with that. So biogenic emissions are a whole range of things. Lots of things can come off of these phytoplankton blooms. Biogenic sulfur is the most well understood. And then the other biogenic emissions, such as diatoms and fatty acids and organic nitrogen, have never actually been identified or quantified in the Ross Sea or even the wider Southern Ocean. So we had two overall goals with this project. The first was that we wanted to understand the sources of these biogenic emissions. So are they coming from the phytoplankton? What species? Are they coming more from blooms or just from the ocean in general? And then we want to understand how they get transported through the atmosphere and then incorporated into the ice cores, because there's some really new exciting work looking at biogenic emissions in ice cores and how they could potentially be a proxy for sea ice extent or primary production, past primary production. And then our second goal was that we wanted to quantify the climate and cloud relevant aerosols in the Ross Sea. And this is really important and relevant because the biggest error in our global climate models, so our models looking at how climate change is going to happen, is from the solar radiation that is reflected and absorbed off these clouds. So without understanding more about our biogenic emissions, we can't fully understand the cloud processes, and then we can't actually accurately model future climate change. So a bit more background about I'm a master's student and I'm writing my thesis at the moment. So it's really important to have knowledge about past phytoplankton change and what's driven that, so that we can make accurate future predictions about phytoplankton change. And our group has developed a new lab protocol to measure biogenic emissions in ice cores and aerosols. And so my project was looking at biomarkers in snow samples from Terra Nova Bay and from McMurdo Sound, and then also comparing that with sediment samples. So here's just a freaky table, but it's pretty simple, I promise. So we have chain length on the left, and then I've just put down all the compounds that I found. Well, I've focused on fatty acids here, which is just the acidic version of a biomarker, because that's the most abundant thing that we find in our samples. And I've just listed all the compounds that are present in the sediments and then in our snow samples. And what's really exciting is that we have this opportunity to compare across environmental archives, so snow and sediment, for the first time. So that's really exciting. But this project, as most projects seem to do, has raised more new questions than it has actually answered. So it's raised questions about fatty acids. Where do they come from? How are they modified in the atmosphere before they are deposited onto the ice? And we also want to know if they play a role in this cloud formation. So I got to go, I was very lucky, I got to go on the Tangaroa as well. And I went with the Canterbury team to achieve a specific objective, which was to deepen the understanding of climate and atmospheric processes through collection of atmospheric measurements and aerosol samples along the voyage track. And we did that so that we could get more data to input into our climate models, and then also to understand the role of these biogenic aerosols. So this is the voyage track, which Svenja already talked about, but I have the colours on this graph just represent chlorophyll abundance. And so that represents, I guess, productivity. So we can see as we get closer to the continent, our productivity goes way up, which Svenja saw in her nets, the whole lot of algae that she found. So I was responsible for a few aerosol instruments, the first being the HiVol. So what we were doing with this was collecting high volume aerosol samples for different biomarkers, so things like fatty acids and biogenic sulfur, and then also for DNA and microplastics. And when we're talking about high volume, we are pumping about 4,000 cubic meters of air through each filter before we swap it and change it for a new one. How we do this is with the HiVol, which is connected to a pump. So this green tube goes off the Monkey Island, which is the top level of the ship, and is attached to a pump in this silver box. And what I think is really cool about this is that it's connected as well to a wind sector control panel, which can turn the pump on and off automatically. So a big problem with aerosol samples is that you often get emissions from the actual boat itself. So the pump would only turn on if the air was not coming from a sector where it would be taking wind from the exhaust and putting it onto our filter. So we were able to, turn it off if the wind was coming from the exhaust, which is pretty cool. And we were doing that so that we can understand the biogenic composition of aerosols and then also their sources by comparing it with the chlorophyll A data, which I showed before, and then also with phytoplankton species that we find in the water. That's a filter. And then this is the map of where our samples came from. So the colors represent a different sample. So each of them are a different sample, and each one was sampled for about 7 days. That's how long it took to get 4,000 cubic meters through a filter. And what I think is quite cool is that some of the filters are representative of quite a localized area. So like the light green one is really concentrated around Cape Wheatstone. So it'll be really interesting to compare that with the light blue one, which seems to be more, I mean, it's still quite coastal, but it's further into the ocean than the Cape Wheatstone one is. So that'll be cool to compare. And then the final aerosol instrument was called the Streaker. And this one also takes aerosol samples. Sorry, this is the second aerosol instrument, not the last. This takes also daily, not daily, it takes aerosol samples, but it takes them daily rather than every 7 days. And we measure trace elements and black carbon, so soot on this. And we do that also using a pump and a control box. This is the control box, and it's quite it sort of works by itself, which is quite good. And every 6 hours, the filter shifts a little bit. So this is the mechanism that it uses to shift, and then it starts pumping air through a new section of the filter. So I thought an image would better show this. You can see each of those little lines is a different 6-hour period. And so some are quite distinctive, like there's some really dark ones. And we'll be able to compare that with back trajectory modeling to see where the air mass came from. So we can see what's actually present on those filters, where it came from, what region it came from. And there is Luke and I. Luke is the Canterbury student that came on board as well. And this is us swapping the filter over in some pretty subpar conditions. It was quite windy, but we managed not to lose anything overboard, so that's a win. And then this is the final aerosol sampling machine that we used. It's quite a small thing, but it is really important. It measures aerosol particulate concentration, so how many particles are actually in the air, and then how big they are. And it's done using a mini laser aerosol spectrometer, and it measures every second. So every second, this black thing that's coming off it, which is going through this box and then they're sitting in this pipe, is sucking air through and then measuring how much there is and how big they are. And this is to understand the physical properties of the aerosol, but it's also to understand where like large biogenic emission events might be occurring. So yeah, we get to see where there are places with more aerosols, where there are different sizes, and when we combine that with the biomarkers and the trace element results, we'll better be able to understand spatial biological hotspots and how that's related to cloud and climate processes as well. So moving on to seawater, I also sampled seawater. We took, using the CTD, this is what we use to sample the ocean. We took water from the surface, so that could be anywhere from 5 to 15 meters, depending on the conditions of the day. And here's me collecting the water into glass bottles, and I put it through this glass filtration device. And then this is a quartz microfiber paper. And as you can see, lots of algae. That's where the color is all coming from. So those will be later analyzed for biomarkers as well. And we're doing that to further understand the sources of these aerosols again. So we're measuring it directly, I guess, from the source that we think it's coming from. And then this is a map of where we took all those samples. And what's really great is that we've got a lot of samples from the same places as those aerosol samples. So along Cape Wheatstone again, we've got 3 samples that we can compare all the different data we have together to see what the whole story is, which is really cool. And then we have a bit of a sub-objective of microplastics. So microplastics have recently been identified in even the most pristine polar regions, which is a little bit frightening. So to analyze that, we took ambient air samples. So I would install this bottle on the railing of the ship, and I would change that every 24 hours. And then I was also taking discrete water samples every 24 hours as well. And we're doing that to better understand, I guess, the spatial and temporal variability of microplastics between New Zealand and Antarctica. And then we also installed a bottle in the mess, so inside the ship, and we would change this once a week, and that's to have sort of a background to compare with the air samples, but it's also so that we can see the microplastic footprint of the boat. So that's quite a cool aspect. So then the other half of the project was more focused on actually measuring the clouds rather than the aerosols. So Luke, the other student, was in charge of a lot of instruments that measured that. But what I got to help with, which was really fun, was the weather balloons. So I was the helium girl, and I got to stand in my little cage every morning, which I actually loved. I really enjoyed it in there. And yeah, what it does is it goes up in the atmosphere and it measures things continuously, like temperature and density and humidity, and it sends it back to the computer. So I would tie on this radio and would send it off into the air. Sometimes it would pop, but most of the time it was successful, so that's good. And here is a map of where those balloons sort of ended up. So what's quite cool, the black dots is where the balloon started, and then the end is when we stopped receiving signal from it. And what you can see is they mostly travel from, never eat soggy Weet-Bix, west to east. They travel from west to east. And that's probably due to the winds coming off the continent, and they blow those balloons really quickly, just off to the east. Really good with my directions. My favorite part about being on the ship was being surrounded by all of these other amazing scientists and people that knew so much more than I did. And I got to learn about everyone else's projects and what everyone was doing. And I got to help with everyone's projects. And I was lucky enough to do an extra experiment while I was on board with Cliff Law. Climate change, we did this because climate change, and specifically the increases in ocean temperature, are predicted to impact the amount of essential fatty acids available to the higher trophic levels, because there'll be less essential fatty acids in the phytoplankton. So to measure that, we simulated, I guess, a higher temperature world. And I still have to obviously look at the results and process the samples to get the actual conclusion of this. But what you can see is that when you increase temperature and iron, there's a whole lot more productivity, as you can see by the color. But what we don't know is whether there's less essential fatty acids in that or not. So that'll be really interesting to look at. So then we've got two main next steps coming off of this voyage. We've got a whole suite of data that needs to be analysed. So we're going to combine it all together to understand the impact of biogenic emissions events on cloud formation and then also the cloud properties. And then secondly, we're going to relate the modern sources to what we observe in the ice core records so that we can better understand the sources and transport pathways that these emissions get incorporated into the ice. And then it's important to note that this voyage was not done in isolation. It was just one of a whole lot of voyages that happened this season that were all looking and measuring atmosphere as well. So all of these voyages will be compared together to get a better understanding of the spatial differences around Antarctica as well. And this is contributing to Picasso, which is looking at cloud and biogeochemistry in the Southern Ocean. And that is me. Thank you.
Thanks, Emma. Any questions from the crowd or online? And we'll do our best to repeat those questions as well for the folks online.
Thank you. Great talk. I really enjoyed it. I was wondering why you chose iron to mix into your experiment. Does it have anything to do with it, like the biogenic markers? Or?
So we'll just try to repeat.
Oh, sorry. Yep.
No. So why did you choose iron? And is that a fair enough sum up? Okay.
So that's an interesting question. I don't think it specifically was a target because of the impact on essential fatty acids, but it's more to kind of continue to explore this idea that iron is a biolimiting nutrient. So it's quite well established now that in places like Antarctica, the biggest limit on growth is iron. So we were just, I guess, using that as a marker of the increases in productivity that we see between the different groups, the different controls, I guess. Yes. So I was just asked when I started my project, did I think there was going to be an atmospheric what? Sorry. An atmospheric component of it. No, I started with ice and sediment. I didn't think that I would be working on atmosphere, but it's a really important link between what is coming off the ocean and what's being incorporated into the ice. So it actually just makes complete sense to be studying that whole pathway so that we can really get a full story of what's happening. I'm all about the story and making sure it all fits in together. Yeah. Thank you. Do I have to?
There's just a comment from the field that there's been an amazing amount of work done here with
Thank
Emma,
you.
so
Thank you.
it's on the record. Brett? So the question is, should we be concerned about aerosols in the air? Basically, here in normal world.
Yeah.
The Antarctic world.
I don't know a whole lot about aerosols and human health and the connections between that, but I do know that you can buy one of these machines that measures the particulate size. So if you're interested, I don't think they're super expensive. You could set one up in your house and see what size particles are floating through the air. Yeah, sorry, I don't know what the impact is on human health. I know that there is an impact because I Googled particulate size this morning, but I didn't read anything about the human health.
I think being in Wellington is helpful. We get a fresh supply every day.
True.
So, yeah. But if you're in a stagnant place, maybe worry about it.
Yeah, yeah.
There's another question.
So you didn't shred any nets, but you did pop some balloons.
We did pop some balloons. So you're supposed to wear latex gloves when you're handling the balloon because any grease or oil can freeze in the air and then like create, I guess, a fracture in the balloon. So there were a few cases where it popped. Some were balloons that I weren't part of, so I'm going to say that that was the reason that they popped. I wasn't the helium person for those ones, so I'm not sure what happened. But the ones that I do know, I think that I was a part of, I think one time someone's helmet hit the balloon, and I think that caused it to pop or some sort of weakness. And then one time we released it, and it went up like 20 meters, and then it popped. So it was released, and then it popped before it could get all the way up. So I'm not sure what happened there. I'm not sure if it had just gotten colder or something happened. It's often due to grease or, yeah, I guess oils. Pardon? Most of them were successful. Yes, 95% were successful. 95, I would say that.
Is there another question?
Yeah, I saw something about the size differences. Like if it's bigger than the size of a hair follicle or something, they use that as a. Oh. That's great.
Well, we'll shut it down there. Anybody online? Any comments or questions? All good? Cool. Thanks, Emma. I suppose I did have one question, but it's basically like you didn't stop working. Is that right? I mean, is it like you're continuously recording and I mean yeah.
Yeah. Some of the instruments were continuously recording.
Yeah, yeah.
Especially the one that was doing the size. That just runs by itself.
Incredible. But yeah, also, and I really appreciate the the approach to the opportunistic and the coordinated opportunistic stuff. That's really amazing and I think underutilized, undervalued, but yeah, super cool. Presents a lot of good opportunities. So thanks for that. So we'll move on to Natalie. Yeah, unprecedented, huh? Let's hear about it.
Kia ora, folk. So those of you who are regular attendees will say, didn't we hear from you last year? And so for that reason, I was a bit hesitant to agree to talk this year. But what I was convinced to talk on was just how unusual this season was that we've just had. So if you are interested in the science, first of all, Svenja has just about covered all we know anyway. But so I'm really going to only cover the science itself pretty lightly this time. But last year's talk is up on our YouTube channel, so if you do want to go back and have a look, it's there. So just getting everybody onto the same page. So map of Antarctica to the left, and then the inset is marked by the red box. And so we're situated in McMurdo Sound, which is not really a sound, but bounded to the west. Emma's nervousness about the directions has thrown me. Bounded to the west by mainland Antarctica, And to the east is bounded by Ross Island, and obviously that's an island which doesn't produce a sound. So it is a sound-ish because it's bounded to the south by the Ross Ice Shelf. So this is a massive floating piece of ice. You can sort of see. The Ross Ice Shelf is about twice the size of New Zealand, and it has the ocean circulating underneath it. And so Ross Island, McMurdo Sound are just right at the northwestern corner of the Ross Ice Shelf. And so there's actually ocean flow coming from under the ice shelf and into McMurdo Sound. So that's why it's not quite a sound, but you get the point. And then the other aspects. So Scott Bay sits at quite an interesting location. So we've everywhere to the north of the ice shelf is at some time open ocean, but come the winter, the atmosphere gets so cold that the ocean itself freezes, and so that forms basically two types of sea ice. So it's ice that's formed in the surface ocean water, and the stuff that is just loose around the ocean we call pack ice. And then there's this land fast ice. So it's ice that is fast to the land. And that is what enables us to do our work. So as you can see, Scott Bay sits right at this intersection between the ice shelf. Obviously it's on the land, but it's also right on the sea ice too. So it's quite an interesting location, and it gives us access to these different types of environment quite easily. And because we're right there by the ice shelf, the water that comes out from underneath actually is super cooled. And I didn't make that up. It has a technical meaning. I mean, it is super cool, but it's below its own freezing temperature, but still liquid. And because of that, it carries with it tiny wee crystals of ice that will grow in that water. So Svenja talked about this already, but so that you get an idea of what it actually looks like. So this white part at the top is the solid sea ice. So we got through about 2 meters of that. And then underneath, these crystals that have come up from the ocean underneath and have just landed against the base of the ice above them to produce this. So there's lots of space between the crystals that's filled with seawater. And so you can imagine it's quite a quiescent environment. There's not big currents ripping through there. So here you can see the individual crystals right at the top of what we call the platelet layer. And this is beautiful crystal clear because there's no biology in it. Yeah, I know. I'll make Svenja stomp. But in this particular year, we had another of these same holes just 70 meters away. And this is what it looked like. So we've got a big deal of variability on quite small scales. So this is really quite swampy. So that quiescent environment plus the sunlight that's coming down from above the sea ice makes for this environment that the algae and potentially everything that the algae supports to thrive. And so that's what we're after. We're sort of after the structure of the platelet ice and any biology that's associated with it. And so for this season, I had quite a large team, for me anyway, 12 people on the ice, and we had quite a large camp. So we had 12 shipping containers. Niwa owns most of these, but they just live at Scott Base and they can get dragged out behind a bulldozer in a train to make our field camp. But there were some interesting aspects, some challenging aspects to this season. So around Antarctica, obviously the temperatures drop in the winter everywhere, and they drop enough that the surface of the ocean freezes over an area that pretty much doubles the size of Antarctica every winter. So you've got this annual cycle, and you can look at it on the right there, where in February you get to your February minimum, and you can see the average area of that in the darker orange colours. And then you've got this period from February through to September where the ice is just growing and growing until it reaches its maximum. so now I've added the variability. I think that's 2 standard deviations over the entire satellite record. So that covers almost all of the different, yeah, you can see that in a year the cycle is quite pronounced. But 2020 turned out to have the lowest September maximum on record for Antarctica. So all around Antarctica there was a bit less sea ice than usual, but it had quite an interesting impact and probably a different mechanism where we were in McMurdo Sound. So coming back to McMurdo Sound, you can see that blue line I've highlighted as the front of the ice shelf, and so often the sea ice will break all the way back to there in February. Not every year, but that's as far as it can go. And then as it grows through the winter, it often fills the southern half of McMurdo Sound. So you've got about 50 kilometres east to west and up to about 30 kilometres is a sort of in the north-south direction is sort of what you've got to play with, and that's what we plan for when we're thinking about where we're going to go. So what happened in 2022? Okay, so we start with February. Now, I will apologise, these images are not that easy to decipher unless you've had a bit of experience. But safe to say that February is pretty much all, the ice that is in the water is loose, and so that's the sort of white streaky stuff that looks like clouds. There isn't any fast ice there in February, so we start from a clean slate. And as we move through the winter, by August is really actually quite late in the winter, you would expect to see pretty much what we just saw with a southern half of McMurdo Sound full of sea ice. Well, not this winter. This was extremely unusual. So just 6 weeks before I was due to take 12 people with me to the ice, there was basically no sea ice in McMurdo Sound. This is all of the fast ice that there was, and obviously we have to work on fast ice. We can't work on the pack ice that's floating around loose. And so if we've only got this tiny wee patch, which is adjacent to Scott Base, so there's actually 2 patches there, one to the north of the Erebus Glacier Tongue, inaccessible for our purposes. So the only piece, and in fact, if we'd planned to go there, that wouldn't have worked either because that did break out in the intervening 6 weeks. So our only option was, our only potential option was this patch, which is about 6 kilometres across, immediately adjacent to Scott Base. And so even though we know that sea ice is there and has been growing there since February, so that little patch is quite stable. As we're having our conversations with Antarctica New Zealand about where we could actually go, they weren't that confident that we could even use that piece of sea ice. So I've got 12 people on tenterhooks wanting to know, and 6 weeks beforehand I couldn't give them a yes or a no. So what was going on? Well, it turned out that 2022 was a winter full of southerly storms. So all of these peaks here, which are happening at about 1 to 2 weekly timescale, all of that is just simply blowing the ice away as it's starting to form. So the ocean temperatures and the atmospheric temperatures probably quite normal, and the sea ice wants to form in its sort of normal way, but with these this continuous southerly storms coming through, I mean, this is what it looks like. You can actually see the ice being blown out. And to give you some scale, so the height of Ross Island in this image is about half of the effect of the wind that's blowing it away. And so Ross Island itself is probably nearly 100 kilometres. And so we're talking about just this powerful wind blowing things clear for nearly 200 kilometres. It just simply didn't have a chance to settle and form. Yeah, so we were about to pull the plug, really. There was just too much uncertainty. We didn't know where we could go. We certainly couldn't go where we had planned to. But then the wind stopped. Stopped for long enough that the sea ice was able to stabilize. And I'll show you. Sorry for the people online. So now we're filling up. So it's this delineation here, which is the edge of the fast ice. I'll explain it again. So basically, it's not so easy to see in this image, but basically we've filled the southern half of McMurdo Sound basically to its normal sort of level with fast ice. But that fast ice has only had 6 weeks to form compared to the usual 7 months prior to when we arrive. So there was no way we were going to be able to take the shipping containers out onto it, no heavy vehicles, but a potential chance that we might be able to travel onto it, depending on what happened when we arrived. And so this happened while we were stuck in Christchurch waiting for our flight to go. So you can obviously see here that there's another southerly storm coming through. You can see that from the streakiness of the northern, the ocean adjacent to the northern half of Ross Island. But what the heartening thing is that it hasn't moved that southern half of McMurdo Sound. So that ice in the southern half is at least stable enough to withstand this storm. Right, so zooming right in now. And so here we've got our patch of what we might call normal sea ice that has been growing and just sitting in situ for about 7 months. And to the north of that, this very young sea ice, which has had less than 6 weeks to form by the time we arrive. So what are we going to do with this unusual situation? Well, we're going to do as much as we can, and it's obviously, I never even showed you where we were planning to go. For those online, we're basically planning to head into the middle of McMurdo Sound in the southern half of it, which was off limits to us. So, yeah, in the final 6 weeks, we finally get a yes, we can go, but what are we going to do with what we've been dealt? So what we decided to do is that we would concentrate our efforts on 2 areas. One array on the old ice, the normal sort of situation, and one array on the new ice. And we'd go and sample the platelet ice as many times as we got a chance to, and basically just compare the structure, the composition, and then the biology associated with these 2 types of ice. And you can imagine there could be quite significant differences, especially when we come to the biology. So if the sea ice in the platelet layer has been forming since February and has formed all the way through the winter, it's had that 6 months of opportunity to sort of recruit. Whereas if we go to the other site where that habitat has only been in place for a number of weeks before we arrive. Sorry, another. I've got a few hats on tonight. Then we could actually be recruiting different species into the habitat. And that's part of the reason why we decided in the end, even though we're not going to be able to do what we had said we would want to do initially, that this was quite an important experiment to go and do whatever we could, because this is potentially looking at a glimpse into the future. And not that we expect sea ice to be forming this late anytime soon on a regular basis, but we certainly expect it to be forming later in the season and potentially thinner. So this was quite a dramatic version, but it will hopefully offer us some endpoints. And then we also did quite a lot of work. So these transects, the coloured lines that you can see, are where we're passively sampling the thickness of the sea ice and the quality of the platelet layer underneath it. And we've made sure to cover quite a bit of both types of ice so that we've got a good comparison between the two. So the question I have been asked, and I don't have an answer, but is it climate change? So when we're comparing what might be our normal year with 2022, is this down to climate change? And as I said, it's likely that the ocean temperatures and the atmospheric temperatures were not significantly different, but that this was due to a different setup in terms of storms. So there's work underway to determine whether that storm setup itself was due to climate change, and could we be seeing more situations like this in future. But what I can say for certain is that there's never been anything like this in the satellite record. So that's more than 40 years of satellite observations, and there's never been a season like this before, which is why I'm calling it unprecedented. On the other hand, the year before, 2016, it was a particularly calm winter, and that was pretty fortunate for me. It was my first time leading a team on the ice, and we just had the run of the place. We literally did 800 kilometres, just going wherever we needed to, and we could do as much wherever we needed to go, because so no one could remember sea ice coming all the way around the north side of Ross Island. So that was also unprecedented. So we've had these two really unusual sea ice seasons in quite a narrow period of time, and recognising also that McMurdo Sound itself is quite variable. So this is all a puzzle that we're trying to untangle. And the other thing to add is that if we look at the trace so far, so that's the blue line that's now added to this graph, we can see it's even lower than the 2022 year in terms of sea ice extent for Antarctica. Now that's probably a legacy of the previous year, so we'll see what happens as it tracks through the year. And quickly, there were some further challenges to deal with. So at least we got to go this year. 2 years ago, the whole season was cancelled. But in terms of COVID planning, we had to be prepared for people to be turned away because they test positive on the morning of departure. So this was quite hard to plan for, and especially for a team of the size that I had 12 people planned to go to the ice. And so for each one of those people, we had to have some sort of backup plan, whether that meant we could cover their task within the existing team or whether we needed to pull someone in from the outside. So in the end, that meant I had to have 16 people all signed up, all with their medicals, their training, their first aid certificates, and all prepared to be in Christchurch at a moment's notice to fly down to Antarctica for 5 weeks, which turned out to be 6 weeks. Well, a week in Christchurch while we waited for a plane to take us south. So yeah, that was challenging enough. When we finally got there, our camp was on the approach to the airfield, which is how one of my colleagues got this image of the RNZAF Boeing 757 flying immediately overhead. It was really quite neat, especially if you're a plane spotter. The frustrating thing was, though, so we flew down, we ended up flying down on this plane, but the C-17s that were required to carry our cargo broke down and did not fly for 2 weeks. And then when they did start flying, of course, we could see them immediately overhead, and we're like, oh, our cargo must be on this one. No. Maybe this one. No. So our cargo arrived in dribs and drabs. It's usually there before we are. And so this particular season, even despite our 1 week delay in Christchurch, the last of it arrived, and actually it was the sampler that was the core of our expedition, arrived 2 weeks after us. So yeah, we ended up with what was supposed to be 3 weeks of sampling condensed into 8 days. So that was a challenge. And then when we did have going to make that was, and here's another. Yeah, it is a southerly. So normally, I mean, we didn't work in this, but normally. Luxury, and it was about 10 degrees colder than usual for this time of year, which, I mean, again, oh, it's Antarctica, you expect it to be cold, but it was cold enough that, so this image shows our sample getting snap frozen in the sampling tube. So this is a matter of 1 to 1.5 seconds of the core barrel dropping down under its own weight to isolate the sample. And in that time, it's snap frozen and our sample has been jammed. So that's just how cold it was. That's not something we had experienced the previous year. But there were some highlights. One highlight is just to actually be able to get on with the science. So it did arrive and we were able to get it out and about. And our unit was able to be dragged. You know, we're pretty mobile with just a Hagland and 2 sledges, so we could go wherever we needed to, and it worked. So we were, yeah. So even with the reduced time frame that we had, we were able to visit 5 sites on each of the old and new ice within those arrays, collect 6 cores, and then by the time you subsample that, they ended up with 48 subsamples on the old ice and 24 on the new ice, because it was, the platelet layer was about half as thick. And then that translated to the biological samples. We handed over to them, and they chose which of those they would sample. So I'm pretty pleased with just how many we managed to bring back. And I have to say, we were all knackered. Everybody put their heart and soul and 120% in to get it done. Just a lovely image. This is one of those cores. So we've gone down in 25 centimeters sections and filtered out, filtered for the algae that's incorporated. And you can see as you go down the core, you've got quite a high concentration at the top and almost nothing at the bottom. So that's really quite illustrative of how the platelet layer works. One of our students, I hadn't even met her before, but she turned out to be quite the lovely artist. So this is her view down one of the microscopes. Another highlight was we were sufficiently early in the season that I was able to see the last sunset from our field camp. I haven't done that before. I've seen it from Scott Base, but not to be set up at our field camp in time for that. So that was actually really lovely. We had a important visitor come to our field camp, and it was lovely to be able to host her. The only thing was that our cargo had finally arrived at 11 o'clock the night before. Yeah. So so some of the crew were desperately trying to get that set up and working, and it wasn't available to actually show her it in action, but yeah, it was great to be able to show her the rest of the camp and the other things we were up to. We had a documentary film crew with us this year who are, yeah, they love Svenja. So they were with us and are working on a full-length documentary feature film, so keep your eye out for that in the next sort of 10 or 12 months. No, that's just another image from inside the container. But the real highlight was the team. We just, you know, it really could have been a disastrous season, but everybody was just so committed, and I had said beforehand, we're just going to have to roll with whatever we got, and everybody just totally took that on board, and supported each other, and just got on with the new plan as it evolved, certainly day by day and sometimes hour by hour, and I just couldn't have been happier with my team. Just really excellent. So we've got a few thanks to give, and I'll just leave you with another of Jackie's lovely images. Yeah.
In the interest of time, we'll just offer one or two short questions. Stefan, please. Ah, we've got two here. All good.
Would you argue that the constant breaking of sea ice that was supposed to be Antarctica is just a giant McMurdo?
Yes, yes. So the question was, would I call that a giant McMurdo polynya? For those of you who know what a polynya is, it's basically an open area within the sea ice. And one of the ways it can form is with the southerly winds blowing it away. So there's always a very large polynya that forms all the way along the front of the Ross Ice Shelf. And so yes, this is definitely polynya type activity. And in fact, I would argue that it's just a westward extension of the normal Ross Sea polynya. We just don't usually see it. Oh, well, you see a little bit of it in McMurdo Sound, just right down near the southern end, but I have never seen anything like that sort of activity in McMurdo Sound. Can I answer it? Can I answer it? So we were fortunate in that the previous year I had for the first time put in a year-round mooring. So that was quite a tricky thing to do. But we did have in the water instruments that were sampling the water all year round. And then when it turned out to be such a weird year, we decided to put it back in so that we can get 2 years of comparative data. So they will be interesting. Yes, yes.
One more here.
We did attempt to do that. Oh, sorry. Yeah, the question was, are we measuring how much light is coming into the platelet layer where we're sampling? So we've collected some of that. We don't do it in the actual hole that we've made because that's obviously not a good measurement. But just adjacent, we'll just get a measurement of how much light is coming through. So you can do that with a light sensor that sits on the surface, so it's measuring how much light is coming in, and then you drill down and put one however far down into the ocean that you're interested in, and you can compare. And it's usually, in this sort of situation, about a 1,000th of the light that's incident onto the surface actually makes it down into the ocean. So it's not a great deal, but these species are very light sensitive. If you actually bring the sample up, it's only a matter of 10 or 15 minutes before it completely bleaches, because they're very much what's the word I want? Tuned to these low light levels. Yeah.
Making the most of it. I mean, a bit like you guys. I mean, making the most of it. Stick-to-itiveness is the word that rings out with your guys' team this year. So we'll move on to Julia here to talk to us about snow. Yeah?
Yes. Yeah.
What happens?
So yeah, I'm Julia, and I would like to talk about snow finally after all the ice talk and ocean talk. So I'm a PhD student associated with the Antarctic Research Center, and I just moved to New Zealand last October and went straight to Antarctica. All right. So my PhD is part of the Marsden funded project, which looks into the influence of snow on Antarctic sea ice. And I would like to just dive into it, starting with the tale of the two poles. So that's an animation of the sea ice formation and evolution in Antarctica on your left-hand side and the Arctic on the right-hand side in 2010 and 2011 throughout a whole year. And just that we are on the same page, Antarctica is a landmass covered by an ice cap and the sea ice is forming around it. Whereas in the Arctic, we have the sea ice formation in the open ocean and it only reaches the landmass surrounding the North Pole in its maximum extent. There are very, very unique differences when we look into the sea ice formation in the two poles. Antarctica on the left-hand side, again, that's a picture from the Sound on January 6th this year, thanks to Jamie who contributed that picture. You can see it's a rather continuous ice mass with a continuous snow cover. There is a big crack, but that's an artificial one because of the icebreaker, which comes to the Sound to supply the stations. Whereas when we look into the Arctic, that's a picture from the Mosaic expedition in August 2020. We can see it's a clearly different situation. We have lots of melt ponds funding on the sea ice, and we have deep blue ocean cracks beneath, and we do have a discontinuous snow cover. So those colors are very important because one parameter which determines or is very important for the energy budget is the albedo, which is the fraction of light reflected by the surface. And snow is a very, very good reflector. So snow on top of the sea ice, on top of the ocean is able to reflect up to 90% of the solar radiation and keeps everything quite cool underneath. So imagine you have your car in the summer, right? And you want it cool. You put up your heat shield. That's basically what the snow cover is for the sea ice. With climate change present these days and increasing temperatures and also increasing ocean heat absorption, we have melt ponds forming on the sea ice, we have bare ice patches, and the albedo decreases down to 30%. If we go further down that road, we can go to below 6% when we have open ocean present. In Antarctica, during our field season, we were actually able to monitor what the albedo does or what the snow cover does to this change in albedo. That's an albedo plot for our expedition from November 8th until the 29th of November. And you can see that in the beginning, we have an albedo around 0.8-ish, then we go down to about 0.76. And then in blue, we have highlighted a very, very abrupt increase in albedo up to 0.86, 0.889, and that was actually a polar storm, which is clearly visible on the next picture. So what happened? We had a nice southerly wind or storm, and it was blowing in lots of drifted snow, which was like settling on top of the old snow cover, and it had a higher albedo, and that's what we could see with our automated radiation station. So coming back to the tale of the two poles, and the sea ice evolution and formation over the years in the Arctic on the right-hand side, you can see that there is a clear negative trend in the winter as for the summer, whereas in Antarctica, we don't really know what's going to happen in the future with the sea ice formation. Is it getting less or is it increasing? There are like more extreme events in the recent past, but the trend is actually not that clear compared to the Arctic one. And that's why we went to Antarctica. That's our research question. Can a persistent snow cover prevent or slow a decline in Antarctic sea ice in response to a warming climate? And we wanted to quantify the optical properties of the snow on Antarctic sea ice. We wanted to quantify the insulation properties of snow and the thermal transfer across the ice-snow atmosphere boundary. And furthermore, in our project, we want to predict the impact of increasing temperatures and changes in the snowpack on Antarctic sea ice evolution. So to wrap that up, it's a bit complicated. What we're going to do, or what we did, we want to do high resolution measurements. That's a 3D micro CT image of a little volume of snow scanned with a computer tomograph. And we do those measurements, like not only that, but we do that in relevant places like the McMurdo Sound, and we combine those measurements, combine them with numerical modeling, and we hope that we are able to predict what's happening in the future with the sea ice in Antarctica. All right, so how do you do that? You send down 4 women to Antarctica. So that's the KO46 team deployed to Scott Base from October to December. That's Roberta on the right-hand side. She's with the Finnish Meteorological Institute in Helsinki. Ružica Daric with the Antarctic Research Center, now working with the SLF, the Snow and Avalanche Institute in Davos, Switzerland. Dao from the Antarctic Research Center, and myself. It was our first time at Scott Base, so we had to undergo all the inductions and we had to go through the Antarctic field training. We had a very nice group of nice men actually with us, and they were like dedicated to build a nice kitchen for us so we could have a nice dinner. So that's how it looks like if they're really motivated. That's our sea ice camp. That's our sea ice camp. So we were deployed for like 4 weeks roughly on the sea ice, 5 kilometers southwest of Scott Base. So we are also weren't in walking distance, but you can do it with a snow machine. Yeah, in an amount of time. And so we had Scott tents, sleeping accommodations. We had this nice neon yellow tent, a polar haven for our cold storage where we would store our drones. We had this yellow rectangular tent with the chimney, which was supposed to be a heated tent for our daily chores and our science experiments. And at one point, we got a heated container because the stove in our heated tent wasn't actually working, and we needed a room where we could have plus 10 degrees Celsius at least, because we had a lot of lithium batteries and they don't like cold at all. So we got a heated container at one point. All right, overview, McMurdo Sound. Natalie already told you a little bit about, or like actually pretty much about the special sea ice formation condition of last year. And for us, this was quite a lucky coincidence because this situation of the old ice, we call it the old ice, by the way, and the new ice. So the old ice with like 2 to 2.5 meter ice thickness and the new ice with 1 to 1.5 meter ice thickness led to a very, very heterogeneous snow cover. And in our original proposal, we wanted to measure 1 location, and we ended up with having 4 because the snow and sea ice conditions were just so unique and heterogeneous that we had the ability to study different things on the sea ice. So that was really, really good for us. And those are aerial images, RGB images of our 4 measurement sites. On the top, we have the campsite on the old ice, characterized by a quite continuous snow cover, 10 to 15-ish centimeter snow depth. We had the rubble site, which was characterized by ridged areas, snow pockets, and bare ice patches. And then we had this like transition site where you can see, so the red dotted line is actually transition ridge between the old and the new ice, with quite different snow physical properties on each side. And then we had 1 test site on the new ice where barely a snow cover was present, and you really had the bare blue ice and just some dirty small snow patches. All right, so we had several things we were doing. First of all, we wanted to monitor the snow cover and the changes in the snow cover as well as in the surface properties of the snow cover. So we assembled automated station and set them up in our main campsite. On the left-hand side, radiation station. The middle is a weather station, and on the right-hand side, it's a Simba buoy, which is able to monitor the temperature of the air, the snow, the ice, and the ocean underneath. The next thing we did, we measured the snow physical properties. And as snow scientists, we love to dig snow pits, right? So that's what we did. We were interested in the surface roughness, in the grain size distribution, the snow density, snow temperature, and we would not do that only once. We would go back almost like every second day or something like that to actually capture the temporal evolution of the change in the snow cover. So that's a first data plot of our automated weather station. I highlighted 2 things. On the left-hand side, you may wonder why there is temperature, but there is no wind speed. So when our stove wasn't working, we had another issue, also cargo related. We didn't have any thermometers. So we ended up assembling our automated weather station inside our tent to actually monitor the temperature in our tent, and that the stove wasn't working. That's why there is no wind speed. And on the right-hand side, you can see this drop in temperature and this increase in wind speed. And that's actually the polar storm event, which I showed you earlier, which was responsible for this change in albedo. Furthermore, we were interested in distribution of the snow cover. That's probably density functions of the snow depth, and it's divided into 3 of our sites. The blue one is the campsite site, where we have a snow depth of about 15 centimeters. The orange one is the ridged area where we have also a uniform distribution of about 20 to 25 centimeters. And then in the transition side, which is really interesting, we have this bimodal distribution, which means the old ice and the new ice had different snow cover characteristics. The depth was different. And that's very exciting that we can see this in our measurements. The second big thing of our expedition were airborne surveys. So we took down drones, like we took drones to Antarctica, which is a tricky thing to do. We had two main drones. One is Spectra, it's the beast on the left-hand side. And then we had the Mattress on the right-hand side, which was for RGB and infrared mapping of the snow surface. And Spectra was used for albedo profiling. I'll tell you in a second how that looks like. If you do drone work anywhere on the planet, you always have to do georeferencing because you need to know where your picture actually is located. So we did a lot of GPS surveys. We had targets on the ground, which will help us to georeference the maps which we produce with the drone imagery. Furthermore, you always have to have ground truth measurements for your drone survey. So that's an infrared sensor, an automated one, which we would put up for every drone flight with the thermal camera so that we can actually have the real temperature, which we can then use for correcting the images from the drone. And that's a very unique thing because I think no one else did it before in Antarctica, at least. So on the right, on the left-hand side, you can see an RGB image of one of our sites with snow machines, humans, and some sensors. On the right-hand side, that's the same area with the thermal camera, and you can see on the temperature scale on the right-hand side that we are speaking about a temperature difference of about 6 degrees. And the snow machines are quite hot, right? We are not interested in the snow machines, obviously. We are interested in the snow. Left-hand side, RGB image, and you can see this dark black patch about 10 meters diameter. And that's a very, very hot target on the right-hand side in a thermal image. And we are speaking here about a temperature difference of about 7 degrees, which is really, really a huge, huge temperature difference. And those images are not processed yet. They are not temperature corrected, but we can clearly see that sediment patches in the snow have a big influence of the overall temperature. The second thing we were interested in, as I mentioned earlier, is albedo and albedo profiling. And Spectra is able to do albedo profiling, which means we put waypoints on snow features like those sediment patches, which are darker and have a lower albedo than the overall snow cover. And we are investigating their influence in different flight heights. So their footprint gets smaller, or the influence of this like snow feature footprints get smaller the more higher you go with your drone. And we just want to know the influence of those features on the snow cover and the sea ice. Yeah, to wrap it up, can a persistent snow cover prevent or slow a decline in Arctic sea ice in response to warming climate? We were able to quantify the optical properties of the snow on Arctic sea ice by doing albedo profiling drone surveys. We set up automated radiation stations and we measured the snow surface properties. We quantified the insulating properties by measuring the density, the snow surface area, the temperature profiles in the snow, probability density functions of the snow depth, and micro-CT analysis of the snow structure. And we will use all this data to improve the model's size and snowpack, or at least to implement some more physical detailed processes. At this point, I'm very grateful about this expedition. We had a rough time. Natalie already explained the conditions weren't perfect. We also had to deal with a lot of logistical issues. I want to thank you, everyone who was part of our expedition, especially the Scott-based staff, who was very supportive and made it happen. We achieved more than 110% of our objectives, and I'm very proud of us that we actually stuck together and did it. And I just really want to thank everyone who made that happen. And if you're interested, there is a YouTube video. Just scan the QR code. It's about our expedition. Right-hand side, that's the QR code for a blog I'm writing about our time in Antarctica, just to make clear how it is to live and work in Antarctica on the sea ice. Thank you very much. I'm very open to answer any questions. Yeah. Yeah. No, yeah, that's the old ice, and we're speaking about 2 to 2.5 meter ice. But that's just the snow surface. So we are only like the drone is just photographing the snow surface. This is not bare ice or anything. So that's just the snow. Yes. Yeah, we were surprised by that actually. As I mentioned, we didn't have any precedent or anything before. So no one, I think, did it before. So we were actually very surprised when we saw this like big temperature difference. And of course, we have to process that and correct it. But I think it will still be very, very huge, like the difference. Yeah. All right. Yeah.
Aircraft often have trouble with icing on the wings.
Yes. Yes. Oh yeah. So the question is if we have problems with icing on the blades of the drones, because that happens sometimes to airplanes. No, we didn't. Fortunately, it's a very big problem in the Arctic though. When they did the Mosaic expedition, when they went with the icebreaker, which was drifting with the sea ice in 2020, they had a lot of issues with that because it was more humid in the Arctic. But Antarctica, as it is a polar desert, is really, really dry, and it's quite good for drones actually. But so what we are trying to do, we have a drone which has a sensor for blade icing. So we would use that one first and see if the conditions are really good, if we were like doubting the conditions. And if that one wouldn't freeze and fall down, then we would take the more expensive ones. Yeah. Yeah. So question is what kind of battery life we were having. Good question, very problematic. So depending on the size of your battery, so our maximum flight time was, I think, 30 minutes, but that was just because we had heated batteries. So the Matris is actually a military drone made to fly in polar conditions. It's the only one available in the world. It's still a pain in the ass, to be honest, because if you don't, you have to put the batteries close to your body to keep them warm, because I didn't do it one time and they just drained, and then you have to heat them up. So it's logistically, it's very challenging, but yeah, the Spectra is having, like, she's working with big lithium batteries without heating, and we have a flight time of roughly 20 minutes. So you only have a small window, and you really have to make it work because they are so sensitive to the cold. It's insane. Yeah, it takes a lot of time. Yeah. Yeah, so we took an army of batteries, and when our stove wasn't working, we would divide them between the four of us and take them into our sleeping bags. Yes. So I usually don't have problems with the cold, but that night was really challenging even for me because I had like this bunch of batteries in the end of my sleeping bag, and just my feet were very cold because I had to heat them up as well. So yeah, yeah, it is challenging. Yeah. Yeah.
It's there were gas and the people
So the question is, the question is if the black spots are actually penguin poop or sediment, right? And if the penguins could actually contribute in melting the sea ice. So no, this stuff like the black spots in our it's sediment actually from Black Island, yeah, and maybe some dust from our and roots from our chimney, but mostly it's sediment from the Black Island. I have no idea about the penguins. I don't think so. I would doubt it. Yeah. All right.
Anybody else? Good stuff.
Mhm.
Amazing. Thank you.
Yeah, you're very welcome.
And, you made me very happy to put the rocks up there. Spot. Good.
Yeah. Well.
Thanks, Julia. And yeah, maybe just one more round for everybody. Hey, like really great stuff. Thanks. Thanks so much. So yeah, so that wraps us up for now. A couple of housekeeping items. If you've got a glass, if you could send it on through that way, back to where it went, I guess. And feel free to take a bite on your way out. There's a couple extra nibbles there, so feel free to crack into that. And last but not least, please take a sticker, take a pamphlet, join the society. There's lots of fun out there for us Antarcticans. So yeah, thanks again.